This is the first video for section 8.4, where we'll be talking about making some trig substitutions. So we're going to be seeing examples of trying to find the integral or antiderivative of something in this form. So we've got a rational function where in the denominator we have the square root of an a squared minus an x squared. So in this general format, a rational function, a denominator, square rooting an a squared minus x squared. We're also going to see different versions of this. Sometimes the two will be added instead of subtracted, and sometimes they'll be subtracted in a different order. And so what we're going to do is we're going to utilize trig equations, sine, cosine, tangent, secant. We're going to utilize trig expressions to make substitutions here so that we can find the antiderivative a little bit more easily. So I'll come back to this example, but let me set up the overall process here. So basically we have three cases. And case one goes back to what I just referred to, where you're going to see the square root of a squared minus x squared. And again, it is going to be in the denominator. It's also possible that you might have a squared minus x squared, let's say to the 3/2 power, meaning that you're square rooting it and then cubing it. So you could see some other versions of rational powers here, not just a square root. But in any case, when we have this format, the first thing we're going to do is we're going to say that x is going to equal the sine of theta. And what I'm going to do is I'm going to draw a right triangle to illustrate the ratio that is presented by this substitution that we're going to make. So if I think about this, whoops, and I forgot my a. Go back and put an a in there. It should be x equals a times the sine of theta. We need to incorporate that a. Anyway, if I go back and I rearrange this ratio here, then I can say that the sine of theta is equal to the ratio of x divided by a. Based on the rules of trigonometry, if I identify a theta somewhere, some acute angle in my right triangle, then x and a have to be my opposite and my hypotenuse sides respectively, because that is the ratio that produces sine. So opposite of theta is going to be x, and then my hypotenuse is going to be a. So let's calculate the adjacent side using the Pythagorean theorem. And what we're going to do is we're going to take x squared plus the adjacent side squared and set it equal to the hypotenuse squared. In order to solve for the adjacent side, we're going to have to subtract the opposite side squared from the hypotenuse squared and then square root. So in other words, if we do the Pythagorean theorem quickly, we'll get that square root of a squared minus x squared. So again, that's why sine is a good ratio to use here, because it produces that format when you solve for the third side of the triangle. So in case one, x is going to equal a times the sine of theta. Something else that we're going to need to know here, let's say we go ahead and replace in this expression, let's replace what x is equal to in terms of the trig function. So let's write this as a squared minus a times the sine of theta squared. And let's continue to rewrite all of this until it's simplified. So if I square that second term, I'll get a squared sine squared theta. Notice both terms under the square root have a squareds in them. So I'm going to factor out that a squared. And then hopefully we're seeing something in this next step that's ringing some bells. We can use a Pythagorean identity to replace 1 minus sine squared theta. We know that that is equal to cosine squared theta. So it turns out that the square root of a squared minus x squared can actually be rewritten, or is equivalent to, the square root of a, whoops, I forgot my square. I didn't bring my square down from the previous step. The square root of a squared cosine squared theta. So again, our substitutions in this case are going to be one substitution. We're going to let x equal a times the sine of theta. And then also we can take the square root of a squared minus x squared and instead write it as this expression right here. We were able to prove that this is an equivalent expression given this x substitution. Let's simplify this before I continue writing it down here. If I square root this entire expression, since each one is a perfect square, it just becomes a times the cosine of theta. So in case 1, I can let x equal a times the sine of theta, and then I can also replace the square root of a squared minus x squared as a cosine theta. So there is my first case. Let's go ahead and do that example that I mentioned in the beginning, which does reference this first case. Okay, so what we want to do is we want to find the antiderivative of dx over the square root of 16 minus x squared. Once again, this is case 1, and we know that it's case 1 based on the order in which we are subtracting a squared minus x squared. So the first thing that we're going to do is we're going to identify what it is that we're going to let x equal and what it is that we're going to let a equal. So I'm calling that step number 1. Well, based on case 1, I should let x equal a times the sine of theta. Notice a squared here is 16, so that means that a had to have been 4, and therefore we're going to let x equal 4 times the sine of theta. So that's step 1. Step 2 is actually going to be to figure out what dx is. And the reason is that in this problem we do have a dx. We're going to be making substitutions so that everything is in terms of theta, and that means that here we need to get rid of dx and turn it into some equivalent d theta. So by taking the derivative of our x expression, we're going to get 4 times the cosine of theta d theta. So there's another substitution we're going to be able to make into our original expression to make it a little simpler. Okay, step number 3 is going to be figure out what 16 minus x squared is going to be substituted with. So again, if x equals 4 times the sine of theta, then all the work that we did up here proved that we can now let that entire square root of a squared minus x squared become a times the cosine of theta. So you don't necessarily have to do this work every time with your specific a value in the problem. It has been proven to work for any a value, so you can go ahead and use the shortcut and just say that the square root of 16 minus x squared is equivalent to 4 cosine theta. Alright, so let's go ahead and substitute. So, instead of dx, I'm going to have 4 cosine theta d theta. And instead of the square root of 16 minus x squared, I'm going to use 4 cosine theta. And so you can see at this point why this process is useful. Why would we even do it? Rather than integrating something that looks like this, kind of a complicated rational expression, we're integrating this expression in terms of cosines, and you'll see lots of cancellation happening in this process. Basically, for all examples, you'll see this nice canceling happening. So really, what we're integrating is d theta. And when we integrate d theta, we just get theta, right? So it's just like integrating 1 with respect to theta. You'll just get 1 theta. And then, of course, plus c because it is an indefinite integral. Our last step is going to be to go back to our x variable. So the original problem asked us to find the antiderivative with respect to x. Well, we found the antiderivative with respect to theta. So we have to resubstitute so that we get our answer in terms of x. Alright, so how do we do that? Let's look for an equation that we've set up that tells us how theta and x are related. And so if we look at the very first thing that we defined, we said that x was equal to 4 times the sine of theta. So all we have to do is take this equation that we set up and we have to solve it for theta. So the first thing I'm going to do is divide both sides by 4. And then to isolate the theta from the sine, I need to use sine inverse. So theta equals the inverse sine of x over 4. And that's exactly, what our antiderivative is here. Okay, so our final answer is the inverse sine of x over 4 plus c. So in the last couple of sections in our book, we've kind of been struggling to do some of these inverse sine, inverse cosine antiderivatives. They're a little bit tricky when you just use sort of common sense trial and error in your head in order to figure out what the correct argument is to give you the correct constant that's found in the original integral. So this is kind of a nice way to take the guessing factor out of it, where we're making direct substitutions and finding that answer a little bit more directly. Alright, so that was case 1. There are 2 more cases, so let's keep going and take a look at what those are. Oops, that was an old sheet of paper that has nothing to do with what we're doing right now. Okay, so case number 2. Case number 2 is going to involve the square root of x squared plus a squared. Or the other way around, because with addition it doesn't matter which order things are added. But instead of a minus sign, we're going to have a plus sign. So let's take a look at which scenario that is derived from. Well, it comes from letting x equal a times the tangent of theta. And if we look at the right triangle, then we know that the tangent of theta is going to equal the ratio of x over a